Thank you very much, Mike, and thanks to everyone for coming out tonight, both here in Kenilworth and, of course, to all those people online. I believe there are some people online, so it's always fantastic to see so many faces to come and hear a talk like this. So, what I'm going to talk about today is, alpine peaks and salt intrusions, but really the interest here is different places in the world. I'm largely going to be talking about Europe, where you can see mantle rocks at the surface. Of course, we think of the mantle as being deep. It's the layer below the Earth's crust. How does it get to the surface? That's what I'm going to talk about. How is it that we can see mantle rocks in various different settings at the Earth's surface? So the pictures that you see here that I'm going to return to several times during the talk, and maybe start with the right-hand side here. This is I think these are among Britain's most beautiful rocks. These are the serpentinites, the sort of blood red serpentinites that are exposed at Kynance Cove, which is a National Trust beach on the west side of the Lizard Peninsula in South Cornwall. They're absolutely exquisite, and they're not, it's all there is at Kynance Cove. These beautiful blood red serpentinites are everywhere. They're cobbles on the beach, big outcrops and exposures. And serpentinite is a type of mantle rock, it's a form of the Earth's mantle. More about that later. And then to jump to somewhere completely different, this is some field work that I participated in, actually in the western part, no, in the eastern part of Switzerland, in the Italian Alps, actually in the Romansh-speaking part of Switzerland. And what you can see here in the background, we worked with this chap here, Professor Gianretto Manaccial, a Romansh speaker, a Romansh native himself. I think his family hail from this area since the 13th century. But what you can see in the background are these scree slopes and indeed whole mountainsides made of dark green rock. And there's often a clue there. Mantle rocks, when you see them at the surface, they have this characteristic dark green appearance. The blood red serpentinites of Kynance Cove, a little bit unusual. You might know that there's several craftspeople in the town of Lizard who are licensed to excavate the serpentinite and turn it into all manner of different trinkets and lighthouses and carvings and paperweights. That tends to be green, tends to be more the kind of color that you're seeing here. Anyway, both examples of places where we can see mantle rocks at the Earth's surface. So without further ado, I shall... What have I done? That one? Yeah. Okay, so I know what I wanted to say. I'm perfectly happy to take questions during the talk. I'm sure we'll have some time for questions after, but if there's something you don't understand or something you're burning to ask during the talk, please just stick your hand up. As they say, and I truly believe it, there's no such thing as a daft question. There really isn't. So let's just remind ourselves what the mantle is. And I love this graphic. Completely unrealistic, produced by the BBC, but it's wonderful, it's dramatic, and it really captures your attention, doesn't it? It was produced by the BBC, I think, to promote the series of programs that Ian Stewart had on earth science and geology quite a good number of years ago now. There's a whole number of much more boring sort of plate tectonic cross sections that I could have used, but I went for, I'm sorry, I'll keep doing this. I went for Dante's Inferno because it's just a lot of fun. So what I think we're looking at here, I think that's the United States that you're meant to be looking at here. Maybe not, because in the middle of the Pacific, no, it can't be. In the middle of the Pacific, we can see an oceanic spreading center. Light runs down the central part of the Atlantic. So maybe the geography is not realistic. Doesn't matter. This top layer here, which we can see being produced at an oceanic ridge and then disappearing down the pan into the bowels of the Earth, a subduction zone here. This is the lithosphere, aka plates. Plate tectonics could also be called lithosphere tectonics. And the upper part of the lithosphere is called the crust, and the lower part is called the mantle. And then below lithosphere, you're into this fire here. Believe me, it's nothing like that in the real Earth, which is the asthenosphere. And just to remind you, so as I say, lithosphere is crust plus mantle. The thickest crust, I should have said, yeah, the lithosphere, about 125 kilometers thick, on average 125 kilometers thick. Remember, lithosphere consists of crust plus mantle. The crust can vary in thickness from 0 kilometers, as you find at spreading centers, to 100 kilometers beneath the mountain belts, beneath places like the Tibet Plateau, the Altiplano of South America. So crust plus mantle, lithosphere, about 125 kilometers thick. This talk is about different places and different processes by which mantle rocks can find their way to the surface. So the mantle is at least 7 kilometers below the surface. And below us here, it would be more like 35 kilometers beneath our feet. You need to go down about 35 kilometers to get to what's called the moho, you might have heard spoken about. And then beneath that, you'd be into mantle. So just a sort of brief reminder on what plates are made of. So here's a close-up of that serpentinite at Kynance Cove that I spoke about. And this slide, you know, if you do one of those courses in presentation skills, this is the kind of slide which they tell you never to produce. This is the kind of slide that's guaranteed to get people huffing and puffing and walking out. But fear not, the only important bit is in the top there in yellow, because I just want to spend a few minutes talking about this beautiful rock, serpentinite, because most of the time, I think maybe all the time in this talk, when I'm talking about mantle rocks at the surface, those mantle rocks have been serpentinized. In other words, the rock type is serpentinite. What is the serpentinization process? Gosh, that's a heck of a word. Like I say, the only important bit is at the top there in yellow. Mantle is made of pyridotite, which you might have seen in outcrop on field trips. If you combine water and pyridotite, then you get serpentinite. You get a range of other byproducts such as brucite, magnetite, and also it's one of the few, possibly the only inorganic sources of hydrogen. Hydrogen is one of the byproducts of the serpentinization process. To add to that, the serpentinization process through what are called these Fischer-Tropsch reactions that convert carbon monoxide and hydrogen into hydrocarbons, it's also an inorganic source of hydrocarbons, of methane, for example. So pyridotite plus water gives us serpentinite. What are some of the other changes that accompany that chemical reaction? Well, I've listed them here. It's an exothermic reaction, so it generates a lot of heat. More of that in a minute. A volume increase, also more of that in a minute. A density reduction, that's significant. This is what seems like a really esoteric point, and that is the velocity of sound waves decreases. But it's really important for us because it means that geophysical techniques like seismic can identify serpentinite in seismic sections. And then lastly, serpentinite is much, much weaker than pyridotite and indeed than rocks like basalt. So a whole number of really important geological processes that accompany serpentinization. And I'm going to try and avoid saying that word as much as I can during this talk. Just dwelling on that conversion of pyridotite into serpentinite, here are some of the geological implications of it. These are just sort of nice little factoids, but some of them are pretty profound, I think. Serpentinization, I said I wouldn't say it again, didn't I? Has the potential to sequester huge, and I won't give you the mass balance equations, but globally significant volumes of carbon dioxide. It's one of nature's carbon capture and storage processes. And there are, there have been plans, not plans, but there have been ideas over the last 10, 20 years to pulverize rocks like serpentinite and peridotite and spread them on agricultural fields the world over because of the ability of peridotite to absorb carbon dioxide. What people have found when they look into it in detail is that the use of carbon in order to drive the machinery to pulverize the peridotite and then ship it all over the world far exceeds the amount of CO2 that you draw down. But it's one of nature's carbon capture and storage processes. I've talked already about the fact that serpentinite is a non-biogenic source of methane. It heats the surrounding rock and just as importantly, the surrounding fluids, particularly water, about 250 degrees centigrade. The heat that you see at black smokers, and do you know what I mean by black smokers? You've seen these extraordinary sort of deep oceanic vents and all sorts of extremophile microbes that you get at those vents. The source of heat for that hot water is the conversion of the peridotite and ultramafic rocks into serpentinite. Serpentinization is implicated in the origin of life, and that would be a whole other story and lecture and PhD in itself, but look it up, really interesting. People like Mike Russell at University of California done a lot of work on how serpentinization, these fluids enriched in methane and hydrogen, could be implicated in earliest life. And I've talked about the fact, that serpentinite is weak compared to basalt and peridotite. So it weakens the lithosphere, and that's really important. I'll return to that later. And then I've talked about the fact that peridotite plus water equals serpentinite. What sort of volumes of water? Well, Mary Fowler, in her wonderful textbook, The Solid Earth, has calculated, she's done some mass balance calculations, just looking at the volume of serpentinite in the world's ocean basins. And she proposes that about every 10 million years, a volume of water equal to the volume of the entire ocean basins circulates through the hydrothermal cells that drive serpentinization. So you might not have heard of this process before, but it's really important geologically. Okay. Part of that, or one of the processes that accompanies the hydration of peridotite, in other words, the addition of water, is that you change minerals like olivine and pyroxene into amphiboles. So in the lizard, some of these amphiboles got beautiful names: antigerite, chrysotile, lizardite. These are all minerals that you can see at places like Kynance Cove. And that's about a 30% volume increase, that hydration process. So what it means is that wherever you see serpentinite, whether it's in outcrops at Kynance Cove or in thin section down a microscope, or this is serpentinite from Davos in Switzerland, it's always cracked and fractured because of that volume increase. So what you can see here are little mineral striations, mineral fibers called slickensides, because those cracks and fractures have moved relative to one another. It's a bit of a mess. And that's because of the volume increase associated with the conversion of olivines and pyroxenes into amphiboles. So let's just go fairly quickly through some of the settings in which we can find serpentinite. So I talked earlier about the fact that, I can't remember what the numbers were, but a significant reduction in density accompanies the conversion of peridotite into serpentinite. And what that means is it becomes a lot more buoyant. It basically floats. It makes the lithosphere much more buoyant. And what this means, we get used to the fact, don't we, that oceanic crust gets subducted. It goes down the pan, around the Pacific Ring of Fire and around Crete and then the Cascadia margin of Northwest America. But there are settings in which oceanic crust can actually be thrust up onto the overriding plate. And that's a process called obduction. And what it results in is geological areas called Ophiolite complexes. And this obduction, this thrusting up rather than subduction, is largely due to the fact that serpentinite is so much more buoyant. The density is so much lower. So two examples there of Ophiolite complexes. You may well have heard of both of them. The Troodos Massif of Cyprus, you might well have been there. And just as intensely studied is an ophiolite, the Samayil ophiolite in Oman. Both places where oceanic crust has been thrust up onto the overriding plate rather than disappearing down a subduction zone.
John,
Yes. Yes.
Serpentinite. Does it have a characteristic colour? Because I know that you talk about the red rocks, and then you showed us the slide with green rocks.
It's normally green. And, you know, you'd need to be a better mineralogist than me to know why the Kynance Cove serpentinite is this gorgeous sort of liver-coloured red, but it's normally green, the alpine example. And I've noticed that the craftspeople in Lizard don't seem to work with the red serpentinite much. They work with the green serpentinite. Maybe that's because it's more popular. Has anyone got any, you know, paperweights or stuff on their mantelpiece made of serpentinite from Lizard? It's beautiful stuff. But it's normally green. Yeah. Yeah, right. And the seams are the fractures associated with the volume increase. Yeah. So Oman and Cyprus, there are other examples around the world. Ophiolite complexes, serpentinite centrally implicated in how they result. Oh, I should have mentioned, we've got our own ophiolite complex in the Lizard of South Cornwall. So what I'm showing here, a couple of pictures of Coverack. Beautiful cove. It's just, let me get it right. It's just there on the east coast of the Lizard. And this photo here is standing at the southern end of Coverack Cove and looking north. We're in the Mantle here, the Mauve Rocks. We cross the Moho, somewhere in here. It's not a plane you can stick your hand on. It's a zone. It's a shear zone. And then at the northern end of Coverack Beach, the green rocks here, we're into crustal rocks. We're into gabbros and sheeted dike complexes. So Coverack, you don't need to go to Oman, you don't need to go to Cyprus, make your way down to the Lizard and you can walk from Mantle, cross the Moho, not at all well exposed, and into oceanic crustal rocks here. So that's another example of an ophiolite complex, in this case related to the Carboniferous Beriscan mountain building event. So we're just going through different settings where you can find mantle rocks. And the photo here on the right is from a field trip that took place last September. In fact, our very own Ray Pratt is there, I believe. This is northern Spain, and we are in the core here. The field group is in the core of a salt diapir. Here it is on the geological map. The salt is Triassic in age, and it's punched through because salt is relatively buoyant and it's quite plastic. You know, in certain circumstances, it can intrude through the overlying sediments. And you can see it has. It's intruded through the overlying sediments. We've got all these radial faults as it's punched its way, literally, not instantly, but by geological creep. It's punched its way through the overlying sediments. The LiDAR image here covers exactly the same area as the geological map. So the fault here is the fault that you can see in the topography. So salt diapirs, all very nice. Why is he talking about salt diapirs? Look, these rocks are green. And you can see on the geological map, there's got these big blobs of blue material in it. And this is peridotite. This is mildly serpentinized mantle rock sitting in a salt intrusion. I should have said where this is. I think I did. Northern Spain. Foothills of the Pyrenees. Not far from Pamplona, where they had the festival of San Fermin and they run the balls and Hemingway lived and everything. But anyway, here we are. In the core of this salt diapir, who would have thought we're looking at mantle rocks? I hope you can see they're sort of faintly green. They're certainly not salt. Ray can vouch for that. What are they doing there? We'll return to that later. And then the last of the settings that I want to talk about before we look in detail at some of the processes, the last of the settings in which you can find mantle rocks is the alpine peaks, bit of my title. So the green rocks here, they've been thrust. You can see the thrust fault. That is a fault there, that distinct horizontal line. Green mantle rocks thrust on top of Mesozoic carbonates, limestones. This is just above the Stelvio Pass, the famous zigzaggy pass in the Italian Alps. This is from the same area as the photo I showed on the title slide. So the Romanche Alps, eastern Switzerland, sort of Italian, border of French-Swiss and Italian-Swiss Alps. And then here we can see, this is the Jakobshorn cable car station above Davos in Switzerland. We can see pods of, again, I hope you can make out, they're dark green. These are pods of serpentinized mantle material, and they're actually offset by a number of faults, normal faults. That's been downthrown relative to that pod, has been downthrown relative to that pod. A bit like books on a bookcase that have been tilted like that. So what are mantle rocks from beneath the ocean doing on top of the Alps? Hopefully, I can use the remainder of this talk to explain that. So there's an enormous amount going on this slide, but just let me take you gradually through it and point out what, the points on this slide that I really want you to focus on. So as I said there in the title, I became interested in this whole area of mantle rocks, not just because it's geologically interesting and they're interesting to look at and they're actually quite beautiful in places, but the last oil and gas job that I had before I worked in the nuclear waste disposal industry, I was lucky enough to work in a team that was exploring in what we call ultra deep water. So by that, I mean we were exploring for not gas, but oil in water 2.5 kilometers deep. So you're right at the feather edge of the continental crust. You go out much further, you go into 3.5 kilometers of water, there's no continent left, you're into oceanic crust. So we're right on the edge of the continent. It was really exciting, frontier, groundbreaking, and exceptionally expensive work for a company to be engaged in. It was very much high risk, high reward. And we became interested, we engaged with people like the Romanche chap I told you about, Gianretto Manaccial, working in the Alps, because we realized from geophysical sections like this, and I'll take you through this in a minute, that the areas where we were exploring in these ultra deep water settings, we weren't very far at all from this serpentinized mantle material. So let me take you through the section on the top there, because that's a lot of background. Let's think about what we're looking at here. This is a It's a seismic section. It's not seismic reflection, which most people have heard about. It's seismic refraction. The difference doesn't really matter, but it's a geophysical reconstruction of what the upper part of the lithosphere and indeed asthenosphere looks like, down to about 25 kilometers depth. So there's the scale. Bear in mind the scale all the time, and it is vertically exaggerated because the horizontal scale there is 25 kilometers. So that horizontal distance is the same as that vertical distance. So it's horizontally exaggerated. It's been squeezed. Okay. This section here, as it says there, is offshore West Africa, offshore Angola. And the basins, the sedimentary basins where we were looking for and indeed found very large volumes of oil are shown, I've labeled by this sag basin here. Okay, what's called a hyper-extended sag basin. Just a lot of jargon, really. Middle Cretaceous salt is shown in yellow. You can see that there. Really weird geometries, a bit more like one of those 1970s lava lamp, because I talked about the salt diapir that me and Ray and others visited in northern Spain. Salt behaves rather oddly once you bury it to depths of about 2 kilometers or more. It starts to become plastic and neutrally buoyant. So it behaves a bit more like geological toothpaste. And the yellow salt here has been squeezed out westward by big delta systems flowing out of the African continent, being pushed out like a rucked up carpet, like toothpaste. So that's why the salt, it's not part of the story here. That's why the salt looks so weird. It's actually been pushed so far out that the salt has actually been pushed out over the oceanic crust. Really odd geological configuration that. Anyway, the basins that we were exploring in these deep water settings, shown here as the sag basin. Crustal rocks are shown in the various brown shades here. Mantle rocks are shown in the green, and the dark green is the asthenosphere that we don't need to worry about. Look, not very far from where we were exploring, you've got mantle rocks at the ancient depositional surface. So suddenly you start to think, mantle so close to the surface, the potential for seawater to get in, you suddenly see where I'm leading with this, the potential to serpentinize that mantle and all the other processes that accompany that I talked about at the start of this talk. The section on the bottom sort of brings in what I showed in the last slide, which was examples of mantle rocks in alpine settings. This is again from Gianretto Manachal, or from his research group, one of his PhD students, Geoffroy Mon, working in University of Strasbourg, who did lots of field work in the Briançonnais region of the French Italian Alps. And this is a reconstructed cross-section through a part of the Alps where he worked. And by reconstructed, I mean, he's getting rid of, he's sort of unraveling the shortening and the alpine deformation. He's trying to think about what it looked like before Africa collided with Europe. He's trying to get an idea of what this ancient continental margin looked like before the alpine mountain building event. And quite a lot of parallels with what we were exploring for in Brazil, in West Africa, in East Africa. Tilted fault blocks that you can see, these little mini grabens, as they're called, little mini rifts filled with sediment. You can see some of them here. But in black, I remember Geoffroy was able to map this stuff, pick it up, see it in the flesh, unlike this geophysical section here, where the interpretation is entirely based on what's called a velocity model. Details don't matter. But between these little rift basins, you've got mantle rocks shown in the black here. So that's when you know that you're really far out. Like I say, you're on the feather edge of the continental crust. Go out much further, and there's no continent left. You're in the ocean. There's the oceanic crust. Continental crust tips out exactly there. That's it, it's gone. It's like a piece of slightly warm putty. You pull it apart, pull it apart, pull it apart. It gets thinner and thinner. It sags, and eventually it breaks. The break is going on there. So remember, I was using this cross section here just to give you an idea of how in deep water Brazil and deep water West Africa, we were exploring in the sorts of settings where peridotite and mantle rocks are getting so close to the surface that seawater can get in and this serpentinization process can begin. Now, in many ways, what I'm going to, just want to check the time. What I'm now going to do is spend a few slides just explaining, just really unraveling that section that I showed there from Angola. And I've always thought that understanding these processes sort of filled in the last part of the plate tectonic jigsaw, if you like. Everyone's familiar with the plate tectonic cycle. It doesn't matter where on the cycle you start. Start with the mountain belt. Mountain belts are actually weak. Continental crust is weaker than mantle. So mountain belts become the nucleus for continental splitting. So you start to have an East Africa rift valley appearing where a mountain belt used to be. Keep stretching, you develop an ocean, like the present day Red Sea. Keep stretching, that ocean gets wider and wider, you get the Atlantic. Keep going, and that ocean begins to subduct, you get a Pacific. And then you get subduction, the continents collide, you're back to mountain belt again. That's what I mean by the plate tectonic cycle, and it goes on forever and ever. But these processes, and let me just take you back to remind you, this understanding how we go from ultra-thin continental crust into oceanic crust, for me is sort of the last part of the jigsaw, the plate tectonic jigsaw. Because this is the kind of section that we used to see not so long ago, actually. Look, we've got rifted, stretched continental crust here, got a continental margin, got lower continental crust, got the mantle in green here. And then they clearly, you know, we, not they, we just didn't know how you went from continent to ocean. But just drawn a vertical line there. Don't know, might as well put a big question mark. How do you make that transition from stretching the continental crust to earliest oceanic crust? And what does that zone actually look like? And to sort of put the answer before you, unsurprisingly, it looks a lot more complicated than you see here. Look, here's the continental crust, faults, rift valleys, and so on. Here's the mantle. Here's the ocean, and the oceanic crust out here. But what's shown in the lower diagram that we don't get in the top diagram, picked out in red, are these very low angle extensional faults. They're often called detachments, okay? And they're increasingly widely recognized. You can see them on land. You can see them in places like the Betic Cordillera in southeast Spain. You can certainly see them on geophysical sections. I'm going to show you some in a minute, but you know, these aren't just a sort of fantasy of geophysics. You can put your hand on them and you can really see them. But you know, I think it is significant that plate tectonics for me kicked off in 1967. That was the Mackenzie and Bird paper where they coined the term, and so it was 50 years old in 2017. It's only really in the last 10 years that we've understood. When I say we, I'm not taking any credit for this. We, the geoscience community, have understood exactly what that transition looks like, because this is a botch, isn't it? Okay, so let's just look at this transition zone in a little bit more detail. So this is a diagram taken from some work by a very sort of forward-thinking US geologist called Roger Buck in the 1990s. Now, we've got what I assume is an oceanic setting here and a normal fault. By that, I mean an extensional fault where the overlying block is going down. The converse of that is a thrust fault, and we're not talking about thrust faults here. So he's drawn, it's all schematics, all a cartoon, a normal fault. Well, what happens if the overlying block just keeps going down? Can't go down and down and down forever. And this underlying block can't go up and up and up forever. What happens is that that fault curls over by a process called flexural isostasy. More jargon that we don't need to concern ourselves with. But look, if we continue movement on that fault, you end up with this kind of configuration here. The active segment of the fault is the bit in red. We've got all these little riders here that are sitting on top of a low angle fault that's now inactive, and that shown in blue is what I called a detachment in the last slide. And we'll see a really nice example of that in a minute. You can't, hopefully you can see, you can't just keep pushing this block down and this shooting up in the air. Something's got to give. This falls back on itself, and essentially we extrude, sort of inject up into that fault deeper rocks from the lower crust and from the mantle. And that's what's signified by these arrows here. So again, you can maybe see what I'm leading at here. This is a method for getting mantle rocks close to the surface. If you continue that extension process, you're going to start extruding the mantle rocks. And the key structures to look for are these low angle detachments. So this is another cartoon from my colleague when I was at the University of Birmingham, Tim Reston, and a student of his called Ken McDermott. And an enormous amount of detail in here, but really what it shows for me is what I call a sort of positive feedback. Once you start this process off, it's self-sustaining. It runs and runs and runs. So let's go from the top diagram down to the bottom diagram. We've got some crust here shown with the stipple and some mantle underneath, and we're stretching it and stretching it and further stretching it. And as we stretch it, faults propagate through the crust into the mantle. We continue to stretch it. These mantle rocks, because we're thinning the stippled rocks, because we're thinning the stippled crustal material above, these mantle rocks get closer and closer to the surface. And you can see a low angle detachment fault here beginning to develop. Continue the process and you have mantle rocks at the surface beneath one of these detachments. You end up with quite a complex geometry, but the complexity doesn't matter. You know, there are as many different geometries that you could see in this kind of setting as there are settings where the mantle is being serpentinized. But the key observations here is that through this process of progressive extension and the formation of low angle detachment faults, we're extruding formerly deeply buried rocks and bringing them to the surface. So that's all very well, you might say. These are cartoons, these are schematics. Where can you see it in real life? Well, you can see it in the Alps, that picture that I showed at the start, and I'm going to return to that at the end. But another seismic section, I'm going to put some color on this in a minute. This is now about 20 years old. Most seismic data, for reasons that are obvious, i.e. expense and sheer logistic complexity, most seismic data are acquired by the oil and gas industry. But this is an example of a patch of real estate off Galicia in northwest Iberia, so north of Portugal, that was recognized to be so interesting in terms of the tectonic processes that an international consortium funded not only acquisition of new seismic data, but a number of research boreholes. These were drilled by the International Ocean Drilling Project. So we've got the seismic data, but we know what's there because these boreholes have drilled into it. Okay, what we can see is some big faults. I'll show some color in a minute, but hopefully you can see just from the raw data. It's processed, but it's raw data without any interpretation. You can see a number of faults, mostly dipping down to the left. You can see a thin sediment fill. This is the water column, a thin sediment fill on top here, and then underneath here, just a noisy mess. So the section I was showing you just then is picked out in the red box. So that very prominent fault block there is the one on the right-hand side of the section. So hopefully you've got yourself oriented. And this is a fully interpreted section, as is clear. And it's interpreted on the basis not only of the seismic data and the velocities and all that kind of stuff, but bear in mind, we've got boreholes from the Ocean Drilling Project that are actually drilling into these structures and recovering to the surface core that can be analyzed, so we know what the rock is made of. Okay, what can we see? We can see some steep faults. We can also see some really quite low angle faults. And look, the green rocks, which is the mantle here, in places, sediment resting directly on mantle. It's resting across one of these detachment faults, which itself has been caught up in subsequent faulting. It's a complicated story, but the details don't matter. We've got these green mantle rocks. There's been so much extension that they've been brought to the surface. We've got sediments, rift sediments, resting on mantle. And here's a couple of examples, I think, of where you can see this in the field. So this is the field guide to that trip to the East Swiss Alps that I showed at the start of this talk. It's a thin section, and what it shows is sediments resting on serpentinized mantle. This is my own field photo from a basin, a Cretaceous basin in the Western Pyrenees near Biarritz, that shows sediments, pretty clear, gravelly, conglomeratic sediments. In this case, not resting on mantle, but resting on granulite facies metamorphic rocks. In other words, lower crustal rocks. Sediment resting on lower crustal rocks in a rift type setting. So this is the kind of evidence you might expect to see in the field if you want to sort of field test the seismic section that I showed there. So what I'm going to do now is I'm going to flip around even this seismic section so that the right is on the left and show it alongside a panoramic photo through the Alps. So that's the same section that we looked at. Remember, it's from offshore Galicia, so sort of north of Portugal, northwest Iberia, further edge of the continental crust. Very similar setting to where we were exploring in these British gas teams, Brazil, Angola, Gabon, also East Africa, Tanzania, for example. The reason why these data, this setting is so much better than it would be for me to show you the Brazilian data is, one, I don't have access to the Brazilian data. Secondly, there's a relatively thin veneer of post-rift sediment on top of these fault blocks, unlike Brazil where there's 3 kilometers of it. So we can see through the sediment relatively easily to what's happening in the underlying basement. That's why this area was focused on by this International Ocean Drilling Project and the accompanying seismic. Anyway, let's go back to the Alps. This is a very similar panorama to the one I showed in the title slide right at the start of my talk, but I've put some detail in here. So you can see the dark green rocks. This is Mantle. Okay, Mantle rocks. These rocks with some vaguely discernible layering in them are labeled post-drift sediments. The blue here, the blue line, is a detachment fault. Okay, and just like we see in the seismic section offshore Galicia, there are places here in the Alps where the serpentinite, the mantle, is not just at the surface today, but it would have been at the surface when this was a continental margin. We know that because there's a detachment fault sitting on top of it, that we've got a thin veneer of post-drift sediments here sitting on the mantle across one of these detachment faults. You can go up to it, you can map it, you can put your hand on the shear zone. It's all there for the taking. So this sort of seismic interpretation backed up by what we can see in the Alps. And so it becomes clear, I think, why companies like British Gas and a lot of other companies that were investing large sums of money in exploration programs in these very hostile, very difficult to access ultra deep water settings, why we collaborated with groups like the Strasbourg group, because really a lot of parallels of what you can see in the field, in the Alps, with what we were seeing in these kinds of deep water settings. So this is one of Giamretto's sections. It's immensely complex, but I'm just going to sort of cut through all the complexity. It really is sort of, if you like, the climax of what I was saying earlier, that this is the last piece of the plate tectonic jigsaw. So this gives us this cartoon here enables us to understand much better how continents split apart, how East Africa will turn into a Red Sea, how one day, tens of millions of years from now, actually oceanic crust will appear along present-day East Africa, and we'll have a new Red Sea. And the Red Sea will be the Atlantic, and the Atlantic will be the Pacific, and so on and so on. Okay, so I'll start at the top. Nice sort of layered mantle overlain by continental crust with some yellow sediments in there. We begin stretching it. You know we're stretching it because the section's getting longer. The continental crust is getting thinner. Lots of nicely well-behaved extensional faults here, but look, some low-angle detachments beginning to appear. And we're bringing closer to the surface lower crustal rocks, like those granulites I showed you from my field photo from the West Pyrenees. But we're also bringing closer to the surface mantle rocks, shown in blue here. Continue that process. The length of the section's got longer. We've stretched it more. Detachments absolutely everywhere. Mantle rocks at the surface, like we saw in the Galicia seismic. And then continue the process. New oceanic crust begins to appear. This is a Red Sea, if you like. This is a sort of incipient spreading ridge with these feather edge continental margins now being conveyor belted outward from a brand new spreading center that's developed in the middle. It's a really nice story that people like the Strasbourg group have put together. I just put this in because you might think, well, where does this salt dye appear? How does that come into the story? Well, hopefully you can see where we are here. There's Galicia, here's northwest Iberia, here's the Bay of Biscay. If you've ever traveled across it on the ferry to Santander or Bilbao, you know it gets pretty stormy. It gets stormy because it's deep water. It's deep water because it's oceanic crust. It's 4,500 meters deep. That area shown in blue there, you're over oceanic crust, hence sperm whales and a whole bunch of other sorts of whales. Inboard of the oceanic crust, what's shown as exhumed mantle, serpentinite. Inboard of that, in pink here, highly stretched continental crust. And then you've got the Pyrenees along here. Well, today's mountain belt was yesterday's ocean, as I said earlier. So the Pyrenees represent an ancient ocean, and the mountains formed when Spain collided with Europe. So we have a similar picture to what you see in present-day Bay of Biscay along the Pyrenees. We would have had exhumed serpentinized mantle rocks along what is now the Pyrenees. They're shown here in green along the trace of the North Pyrenean Fault, which is the suture between Spain to the south and Europe to the north. So it's easy to see how salt diapirs, and the one I showed you sits along the Pamplona Fault. It's about here. It's easy to see how salt diapirs could incorporate pieces of exhumed serpentinized mantle. So that's, in a nutshell, what those mantle rocks are doing caught up in a salt diapir. Appears bizarre to start with, but actually there's some sense in it. So I just want to spend the remainder of my talk. How long do you normally speak for? I won't be much longer. I talked about the fact that, central to all the processes at continental margins is you're thinning the crust. If you thin the crust, it subsides. Subsides a lot. And in the case of the South Atlantic, and remember, we were exploring in Northeast Brazil. Where are we here? Hopefully you can make out the outline of South America here. Hopefully. This is a reconstruction back to Aptian times, Middle Cretaceous. Hopefully you can also make out the outline of Africa here. Look, here's the East Africa rift system. And here's the incipient Atlantic beginning to develop between the African continent and the South American continent. Now, the South Atlantic unzipped from south to north. I'm going to show a little plate tectonic animation in a minute, but sadly, the online Zoom people won't be able to see, but bear with me. The South Atlantic unzipped from south to north. So during Middle Cretaceous times, you had new oceanic crust forming between, let's say, Argentina and Uruguay, and Angola and Namibia. And then there was a barrier called the Walvis Ridge, or in Brazil, it's called the Florianopolis Fault Zone. And to the north of that barrier, we had stretching, but we didn't have oceanic crust. So everything went down and down and down. Why have I shown a picture of Death Valley? I could equally show a picture of the Dead Sea. It's because this area picked out in red here, very similar to present-day Death Valley, but on a scale vastly greater. This would have been a salt basin at least 1,500 meters below sea level, fiercely hot, fiercely hostile environment. Hence, I bring in Death Valley as one of the best analogues. I'll show some others in a minute that I can think of. The colors here, Death Valley is shown in here. The colors, for your amusement, are daytime temperatures or surface temperatures at, look at 20 to 11 at night, 30 degrees. We all know Death Valley's hot. Why is it hot? Because it's in a continental interior and it's so low and it's salty and all that radiating rock around you. What I'm trying to say is because of this stretching process that took place before Africa and South America finally rifted apart, we had the big daddy of all Death Valleys sitting here all the way from northern Uruguay all the way up to the on the African side up to Cameroon and Equatorial Guinea and that area, an absolutely humongously enormous Death Valley. What would it have been like? Well, it would have been hot. There would have been alkaline groundwater springs developing these calc tufa towers that you can see in that sag basin that I talked about earlier that we were exploring in Brazil. Some analogues here, Pyramid Lake in Nevada. It's on sacred North American Indian land, so difficult to visit. Mono Lake on the eastern side of Yosemite Valley. you might well have been to. These are pictures I took from a family holiday there. But these are all good examples, if somewhat smaller, of that vast salt lake that existed between South America and Africa, with these towers of talc tufa, all sorts of weird and wonderful minerals. We in British Gas were very concerned with a clay mineral called Stevensite that occluded it sort of destroyed the porosity in the reservoir that we were targeting. Stevensite only forms in alkalinities of pH 12 or greater. So the quote here, and if you can't see it at the back, I shall read it, is from my colleague Paul Wright, who worked a lot on these microbialite lakes, the Brazilian, the Cretaceous lakes. The microbialite lakes would have been a caustic hell on earth, fed by hot springs, like the biggest wash tub in Earth history. Although the lakes were at ambient temperatures, away from the vents, they were still alkaline enough to peel skin. We know that because of the presence of this weird Stevensite mineral. And, you know, just to take you back to why I'm talking about this kind of setting, it's because of the hyperextension that I talked about in the context of bringing mantle rock to the surface. You stretch the crust enough, it subsides enough, so you develop these huge sort of Death Valley type low ground. So I just want to show, for the benefit of those in the room, and apologies, this is the last thing I'm going to show. So if you're online, just bear with me. So this is a program. It's not mimicking what's on my screen, Gareth. If it doesn't, it doesn't. I've only got one HDMI port. If it doesn't work, it doesn't matter. Oh, oh. I must learn that trick. So what you did was switched it off and switched it on again, yeah? Yeah. Got it. So this is a program called G-Plates. Apologies for those who are online. And it's just a really neat little plate tectonic animation that so we've got present day topography on the continents. I've wound the clock back here to about 200 million years. So when the Gondwana continent was still fully assembled. I'm just going to play it forward, and what we're particularly interested in is just to understand, you know, the sequence of rifting in the South Atlantic. Clearly you can make out Africa, South America. The program is purely based on what's called the oceanic isochrons, so the sequential ages of the oceanic crust. So you'll see what I mean. I'm just winding it on by hand. So the Gondwana land is beginning to split. So Antarctica's on its way. New oceanic crust beginning to form in East Africa. India's just about to absolutely sprint northward. So if I stop it there, you can see the South Atlantic. It's beginning to open. We've got new oceanic crust appearing. This is that salt lake, that microbialite lake that I talked about. And this only evolves into an ocean a few tens of millions of years later. So at this kind of time, 140 million years, so Aptian Albion times, this would have been the time when we had this giant Death Valley. There's a heck of a gap here because of something called the Cretaceous magnetic quiet zone, when there wasn't a flip in the Earth's poles. But so at that point, by the time we're to 80 million years ago, for sure, oceanic crust existed between Africa and South America. But it's this point here that I was talking about, that big lake system to the north of the Walvis Ridge, the Florianopolis fault zone, extending all the way from sort of North Uruguay up to the, this corner of South America, Cameroon, Equatorial Guinea, and then that eventually evolved into. Pardon? You asked about the Red Sea, yeah? Let's see. I mean, because there's so little oceanic crust in the Red Sea, it's not, it's opening a little bit there, but you've not got much time to play with. Look, by the time you go back to, what's that, early Miocene times, the Red Sea, there was no oceanic crust in the Red Sea. Anyway, I don't want to get stuck in G plates, but it just sort of puts a little gloss on this idea that that we had this big sort of Death Valley type. Let's come up with my screensaver now. This big Death Valley in the South Atlantic. So I'm going to leave it there, and thanks very much for coming. Thanks for your attention and for the questions, and I'm happy to take any questions that you might have. So thank you very much.